And good morning, everybody, and thank also Johan to have invited me here. Just to be very clear, of course, he exaggerated large, very obviously. Okay, so I will talk about the long journey to the Higgs boson, and if time permits, even what comes beyond at the LHC. And indeed, I will go a little bit over historical moments, historical facts where we learned how to do these experiments. So let me say very clearly, this is not really a serious lecture. They only come afterwards. I have the privilege to give you some highlights or so. So this morning you can still relax. If I would have to say one single thing about the LHC project, then I would probably say that it is really a global science adventure which has combined and is combining the accelerator on one hand, the computing, very important. I will be only short on that, but still. And of course the experiments. And this was initiated, well, now more than 30 years ago. And as Hans said, given my age, I was working since the beginning on these things, and I find it quite a great privilege to show you actually some results which came out finally. But let me give you a little bit a naive motivation for this project. Why are we so excited about it? Well, in a certain sense, it actually connects on a ruler which has on one hand the size of the universe and the smallest distances from the Big Bang. It makes a synthesis between this. Well, human scale is conveniently in the middle here. So the universe, as you all know, we of course explore with telescope, either Earth-based or space-based. What we are doing in particle physics, we go in the other direction, looking at smallest distances, and distances typically 10 to the minus 16 seconds or centimeters. So actually, sometimes people say, well, the Large Hadron Collider, of which I will talk about much more, can be seen as a super microscope. And clearly, there is a synthesis of what we learn here, which has to do with how we understand the universe. We can look this on in another way. This is kind of a history in a very non-linear scale of the universe from the Big Bang to today, something like 13, 14 billion years now. And what we do with accelerators, and in particular the LHC, is to reproduce the conditions which happened very shortly after the Big Bang, typically 10 to the minus 11 seconds or so on this scale. And so, just to say it in a global way, with the Large Hadron Collider at CERN, we can really study the physics, the fundamental physics, in conditions which we can control, and with measurements which we can reproduce. That's the basic of working in science, that we can actually verify measurements and so on. So just to show you what we do, and you're certainly, most of you are familiar with that, but nevertheless, let me show you this little animation. So in the LHC, in a tunnel, I will talk about that, we accelerate protons in two directions. The protons are composed of quarks, gluons. These are the particles really colliding. Then we have these instruments, for example, here the ATLAS experiment, where we bring these particles into collision. And what we examine are the collision products. And that gives us information about this highest energy behavior of matter. Just to introduce also very briefly what I will talk about and use all the time, namely the ingredients of the standard model for particle physics. Well, you have here a sketch where you see in first place the three families of the matter particles, the quarks and the leptons. We have the interactions between these fundamental constituents. Actually, of the four known interactions, three of them are of the standard model. They can be described by what is called quantum field theories. This is not yet achieved for gravitation, and many people are working on that very strongly. Now, you see here also already indicated a third element, which is the Higgs field. I will say more about that, which solves the problem of how actually these particles get the mass and why some, like the photon, doesn't have a mass. So, stepping back, already in well, many generations of colliders, of experiments at also previous generation of colliders, were motivated by looking for this Higgs particle and looking for a way to prove this very bold theory which was put forward by Brout and Englert, Peter Higgs, and some other gentlemen, which brought forward this theory in the 1964 or so. Now, here is another picture of the standard model, maybe a bit more useful for you to find your way. Again, the three families of the matter particles, they have a quantity, a quantum number, which is called spin, which is half integer, and they are called fermions. Then there are the particles which are responsible for exchanging the forces. They are characterized by an integer spin, and therefore are called bosons. And then there is this very special guy which has a spin 0, integer. There's also a boson, which is the Higgs boson. So just to remind you, of course, now a couple of years ago, this story, this search for the understanding in the standard model, this hypothesis about the symmetry breaking or the mass mechanism, has come to a first happy end, in particular for François Englert and Peter Higgs. It's interesting to see in the Nobel citation that very explicitly the ATLAS and CMS experiments are mentioned, because clearly these gentlemen had to wait so long to get their prize before it was really experimentally confirmed. Unfortunately, Robert Brout died just 2 years before this. So I will, of course, not really talk here about the mathematics of the standard model. I can just show this, that there is mathematics behind, and here we see François Englert pointing out the important part in this Lagrangian, which describes, in a way, the interactions between all these particles. Now, just a short explanation. Why do we actually need a Higgs particle? Well, elementary particles, by definition, are point-like, without the internal structure, and so the natural thing would have been to assume that they don't have any mass. But we know from the experiments, we'll come to that, one Hans was mentioning, for example, the W-Z bosons, they have a very large mass, 80, 90 GeV, whereas the photon has indeed zero mass. So the symmetry is broken, and that was really the puzzle that Peter Higgs and company tried to solve with the hypothesis of a field. Now, this proposition they made had many theoretical implications, and I guess you will hear more about the Higgs potential and so in following lectures. But what concerns us, and a naive experimentalist like me, is that it predicted that there should be a new elementary scalar particle, scalar because of a boson and spin zero, so that's called a scalar. But the mass was not predicted. So we needed to make an experiment where we can look for it in a very large range of masses. And the discovery of this particle then would really verify this theory, and that's exactly what has happened. Just for your fun, if you want to learn about the Standard Model in terms of comic strips, I recommend this here. It explains very well that in this field, well, massless particles, light particles, they go through it very fast. This is, of course, only an image, whereas heavy particles, they are slowed down in the field. They have a hard time to move and so on. It's a good analogy, but of course it's only an image. Now, just to be very clear, also that we're talking for the Higgs particle has to do with the mass, but it has to do with very little of the mass actually. It has to do only with about 800 grams of my mass, because most of the mass comes from the binding of the binding energy in a certain way. You can say from the quarks, gluons in the proton, neutron. Well, that's most of the mass of us, of course, what concerns us. And this also tells us that the proton and the neutrons actually, for example, they are not elementary particles. So when we collide protons, we are not colliding initially elementary particles. We collide actually the constituents inside them. So by chance, this quark model, which is very well verified, also has been put forward in 1964. So this was a very important year. So what happens actually in these collisions? The LHC is a very complex thing. I just said there are quarks, gluons. There are also virtual quark, anti-quark pairs in the proton. And well, sometimes two of them really collide very hard, and the others, they make some scattering, some other soft collision, as we call them. So one can say sometimes the collisions at the LHC are very, very messy, and it's difficult to find some special events out of them. So in a way, what we're looking at is, again, to take up this picture, we collide in an elementary way two constituents, for example, two gluons, which can make, through a loop process, I will mention later on, a Higgs particle, which in turn decays again into other particles, which we finally see in the experiment. But there are other constituents which are present in these proton-proton collisions. And just to tell you, when we draw such pictures, they actually, this way of describing particle collisions, elementary particle collisions, we use a picture put forward by Richard Feynman, some of the best lectures you could ever find in particle physics, where he has found a way to describe, here is a very simple topology where we would collide two elementary particles, an electron and a positron, which annihilate in a photon, which then produce a quark-anti-quark pair, and here's a gluon which is radiated. So that's the way we describe these processes, and there are also rules how to calculate the probability that they happen and so on. Okay, so that was a little bit of background information, and now about how it came that the LHC was, how was it put on the rails, and that actually happened already. Well, first ideas that one could put a Large Hadron Collider in the Geneva area, where we have CERN, were already mentioned in the 70s, when one was discussing a previous machine, but at that time also only a project, namely the Large Electron Positron Collider, called LEP. You may have heard about that. So LEP was approved in 1981 with a large and long tunnel, already having in mind that eventually it could be useful for a hadron collider. But at that time, people were very skeptical that with these composited proton collisions, one could actually do discovery physics. Just for the fact I said, these are not elementary, they are composite, so there could be a lot of mess, and we saw some pictures of this mess. But then came in '83 the discovery, I will say more about that, of UA1, UA2, for example, of the W and the Z boson. And they were very clean signature. This is actually the signature for a Z boson decaying into a E plus C minus. And what is shown here is the energy distribution in the calorimeter. Well, the sphere is put on a plane, and you see that this is a phi which is something like 180 degrees opposite each other. So this was very clean to see among the other events. And so at that moment, immediately people said, no, we can use a proton collider to actually also discover new physics. And so in '84 then was really the start of LHC, because at the workshop in Lausanne, there came theorists, experimentalists, and machine builders, and for the first time really discussed how one could use the LEP tunnel later on to build a hadron collider. There were further discussions, like a bit now, history repeats, because there was still also, of course, a community which said maybe we should make E plus E minus collisions, and already at that time. Now, just to give you a little flavor of the 80s, in the 80s technologies were still different. People were writing transparencies in the sense of really writing like that. And we started thinking, how would one do an experiment? Well, one could make an experiment where we only see muons, because that would be the easiest, just having an absorber around the collision point and just see events where only muons go through. This is the only particle which goes through big amounts of matter, as you will learn later on. So one could see the Higgs when it decays, for example, in 2Z and then 4 muons. But that will be all. So we were thinking of making more and more sophisticated experiments. We didn't really know how to do it, but we were courageous. And as you will see, now the detectors are really very sophisticated and can handle all these different final states, electrons, muons, taus, jets, missing transverse energy, and so on. But just to tell you, the 1987 was very crucial because in the comparison between a proton-proton collider and a large E plus E minus collider, finally the recommendation was to build the LHC, thinking that this has the highest potential for making discoveries at that time. So, well, there were more studies. I will not go into them, but then in October 92, finally two big collaboration started seeing, well, it came into existence. And Atlas and CMS, and they started really by presenting in documents which are called letters of intent, their intentions to build experiments at this machine. And indeed, in October 2012, our spokesperson at that time, Fabiola Gianotti, celebrated the 20 years of Atlas. Now, that was just the beginning. Then there was a long time of huge amount of design work, of tests with prototypes and so, before we could convince the committees that actually Atlas and CMS should be built. And this happened really at the end of 95, officially in the beginning of 96. So this was a historical document I got from the peer review committee, which says official leak. And I think that's after that the first time I could sleep a bit more quietly, knowing that, okay, now Atlas will be built. But then it was still a long way because, okay, 95, we had, of course, to convince the funding agencies all over the world participating, in this case in the Atlas, but similarly for CMS, to finance the experiment. And as you can see, it took, this is this expenditure of money. Maybe one should also once show this. As we had foreseen in 95, well, we did build it a bit slower, so we spent less. This is the red curve. But then at some moment, we also saw that it's a bit more expensive, and we spent a bit more. But this gives you, in a way, the time span it took to build, actually, the experiment. So from 95, essentially, to 208. Now, at the same time, so this was the experiment. Of course, at CERN, the member states of CERN also had to agree to build the machine, which is even more expensive. And this happened in parallel. The decision to build the LHC was taken in the council in December 94. At that time, I say the machine was even more expensive, indeed too expensive. So what was approved was not the full LHC, but the LHC which would have had some elements, some magnets, staged. So it was a two-stage machine. But it was said that if one would find money from other countries which are not in Europe, not CERN members, then one could go ahead and build the final machine in one stage. And that actually happened. So there was a long campaign, several years, to convince Japan, Russia, India, Canada, and particularly also the US, to contribute to the machine. And indeed, in '96, then the LHC as we know it now was approved for construction. And this picture, for example, shows you elements built, in this case in Russia, which are now operational in the accelerator complex of the LHC. So what is the LHC? Well, first of all, in the 90s, it was a very nice girls' band, which I liked a lot, Les Horribles Cernettes. And actually, this has some relevance because it's arguably the first picture which was put on the web. The web was also initiated in the 90s, 92, and okay. So the LHC is the Hadron Collider, which is housed in the former lab tunnel, 27 kilometers, about 100 meters underground. And I will talk also a little bit and compare with the CERN P/P collider, which Hans already mentioned. This is the SPS, in which one could actually collide protons and antiprotons, and which was used to find the W and the Z in particular. Maybe about accelerators, just to say briefly, there is really, in terms of energy, as a function of the years, a steady evolution. It's called the Livingston chart. You can look that up. What is interesting to see is that really the last machines, they are all were only possible thanks to superconductivity, to reach high magnetic fields in order to keep the particles on their racetrack in a finite size tunnel. Just again a flashback. This was the first ring collider by Lorentz, 1930. Then a very famous machine was the Berkeley Bevatron, seen here. And the first real Hadron Collider came then in the 70s to the early 80s at the CERN proton-proton intersecting storage ring, the ISR. And you can see at that time one was actually building a machine such were two different accelerator rings. This is one ring, this is the other ring, and this is the crossing point. And it is at these crossing points that the experiments then were installed. And that Hans was alluding to, this is one of the experiments which was installed there. So this is Hans here. And that's the famous muon magnet which he was responsible for. Now, what you can see is there is a lot of space which is not instrumented. And that is something one has learned, that of course, if you want to make an experiment for finding something like the Higgs, this would essentially be impossible to do with such an experiment. And indeed, we have paid somehow this mistake, because the LHC, the ISR could have discovered the J-psi meson, which was discovered in the 74, a few years before, because if you waited long enough, you did finally extract a very nice signal. But if you would have had a complete experiment from the beginning, this would have been a possible discovery for CERN. Then came the next generation of experiments, and so we have already learned that one should, in principle, have an experiment which covers all the solid angle. And so the next generation then were at the CERN P/P collider. This is at this injector machine at the SPS, as I mentioned. And then Hans played here a very crucial role. Well, it's a box, essentially. That's the UA1 experiment. This is the UA2 experiment where, well, I was in that one. We had not enough resources, and so we still had a lot of non-instrumented parts. We tried to change this by an upgrade in the second half of the 80s by making new calorimeters to be more hermetic. The third of these four colliders, which I pointed out on the Levinson plot, is the Tevatron at Fermilab. This is a superconducting proton-antiproton collider, which did run for a very long time, as you can see, from 83 in a way to 211. One learned against this machine. First of all, already the experiments were much more sophisticated, but what one learned is you have really to put a lot of care into making the collider performing well in order to produce good physics. This can be seen here over this period of long period. Actually, they were producing very little integrated luminosity, which means integrated number of collisions. You see only in these units 0.12 inverse femtobarn compared to later on where they have finally produced 10 inverse femtobarn. So it was very difficult in a way for the experiments in the beginning to find something new, because the cross-section, the probability that it would happen is very small at these energies. It's a 2 TeV machine, and so you need really a lot of collisions, and they did not have enough collisions. So this was also a lesson one learned. On the other hand, they were very pioneering in having really complete coverage in the experiments, and they developed also a lot of the methods how we analyze now at the LHC the data. So let me come back to the LHC. The LHC is, well, it's not only the main ring, but it also is a very complicated arrangement of all these pre-accelerators which are needed to bring the protons into collision. Now, the main elements of the LHC are supraconducting dipole magnets. They are 1,232, they are 15 meter long. And these here are the two beam pipes. Normally in the arcs, the beams are about 25 centimeters apart, and then they are brought on collision course at the experiments. So the field, which is done, as I said, by supraconductor, is very large. It's about 8.4 Tesla, which is achieved with a current of 12 kiloamps. And if you use this formula about the bending and the field and the radius, you can see that with the LHC one can achieve beams of 7 TeV. That means 14 TeV collisions at the end. One of the big issues for this LHC magnets is that they're superconducting, so they have to be cooled. They're cooled actually to 1.9 degree Kelvin. And just again a flashback, one can say that it is more than a century ago, actually, that liquid helium was for the first time obtained, of course, a very, very small quantity, whereas the LHC now has a huge quantity of liquefied helium in order to cool the whole machine. The construction of the LHC took a long time. In fact, this is January 2001, and then January 2008. And you can see, without going into any details, clearly after some learning period, it took several years to construct and install the machine. Now, I mentioned the magnets to keep the particles on the racetrack. You also have to accelerate them, and they are accelerated by making a electromagnetic field such that every time when the proton goes through, they get a little kick. And of course, the frequency changes a bit the higher the energy comes. So it's quite a complicated thing. And in fact, that's how they look like. That's how these supraconducting cavities, which create the synchronous electromagnetic field to accelerate the particles, look like. They are installed at this point on the LHC, point number 4. And finally, another very important element is to focalize the beams, because I mentioned already, actually we look for very rare events, so we need a lot of collisions. So these are lenses, quadrupole magnets. Again, I assume you will hear more about that. And they are focalized the beam such that at the point where the experiments are installed, we have a higher probability of having collisions. You can also see that, by the way, these are typical elements which are built by non-CERN member states from this period where we had to get contributions from other countries. This is from the US and this is from Japan. Now, just to tell you that what we were looking at and searching for is occurring very, very seldomly, rarely, in comparison with the normal interactions of two protons. So you see this is a logarithmic scale. We have to go down many orders of magnitude, for example, to find the cross-section, the probability to produce, for example, Higgs or even a heavy Z, a Z prime, or things like that. So this is something you can look at maybe in leisure afterwards. So the point I want to make is that you need really very dense beams. For example, ultimately the machine will have something like 2,800 bunches going in one direction, 2,800 in the other one. Each one has already now more than 10 to the 11 protons. The reason for that is that, for example, a Higgs particle, which we will talk about, is only occurring in an observable way 1 in 10 to the 13 collisions. So you have to examine really a lot of collisions to find them. And this also means you need very sophisticated instruments to find them. Maybe very shortly, just what is these particle detectors? You will hear much more. That's, of course, the topic of your lectures you will have. What one typically does is one surrounds the point where the protons collide by different layers of particle detectors. Inside, to see the charged tracks, for example, from the collision. Then to have what we call calorimeters, electromagnetic and hadronic calorimeters, to measure the direction and the energies of electromagnetically interacting particles like electron, positron, photons, typically, or the pions in the hadronic calorimeter. And then what is shown here in red is large spectrometers to measure the only charged particles which go really through the whole detector, the muons. So these detectors have a dual role. They have, in a way, to select potentially interesting collisions very quickly, and then for these to provide as much information as possible from the collision for the analysis later on. So at the start of the LHC in the 90s, this was a list of typical questions one wanted to address with the LHC, being aware that the standard model is not really complete, that there are open questions. At that time, what was the origin of the masses, as I already mentioned, but then many others, like what is the nature of the dark matter in the universe? Why do we see much more matter and essentially no antimatter in the universe, which is not very logical and is not understood? Then also other questions, what happened a bit later after the Big Bang? How did the hadronic matter really come about? And so on. And then, of course, there are also many ideas about additional super strong forces, for example, additional space dimensions and so on. So finally, one decided that there would be 4 big experiments which should address these questions. And 2 of them, the very big ones, ATLAS and CMS, they are called general purpose detectors, which would mainly address these questions here. Then a specialized experiment, LHCb, for this matter-antimatter puzzle, and ALICE to look more at the quark-gluon plasma. And as you know from this catalog, only the first one we have just starting to tick off. So here is a picture of the specialized detectors, LHCb and ALICE. I will show you another picture of that. This is the ALICE detector, a bit difficult to see. In fact, the ALICE detector is a bit special because it's the collisions, they happen here, asymmetric, and then it is one direction, a forward cone, which is instrumented and is in particular instrumented to also be able to see finite lifetimes of particles, like the B quark decays after a few millimeters typically if they have a certain boost, and it's a speciality of this experiment to look at such topologies. Another experiment I will unfortunately not have time to talk about is ALICE, which looks at the quark-gluon plasma. This is a picture of this detector. So I will talk now more about the general purpose experiments, ATLAS and CMS. And they have something very interesting, namely a completely complementary technologies were used. It was important, as I said in the beginning, that you can verify measurements, and in particular if you pretend to have made a discovery, it's always good to have an independent measurement. And to have independent measurements, the best is, of course, if you don't use twice the same detector, because you could have some systematic mistake in one of the detectors which fakes a discovery. So the best is if they are as orthogonal in a certain sense as possible, but of course both should be really capable of seeing what you want to see. So that was kind of the basic criteria when CERN selected the 2 big experiments. There were other ideas around, but okay, ATLAS and CMS, they were then retained. So in fact, CMS is based on a large solenoid magnet. Well, this is showing here the how the current flows in a solenoid, and then this, the blue is the field line. And Atlas was just different. It has a large toroid magnet. Again, in red are where the current flows, and then the magnetic field goes around it like a toroid. So this is a picture of CMS, and I will go a little bit fast about these things. You see here the solenoid magnet, and then these different layers of detectors. For example, the electromagnetic calorimeter, the tracking detector inside and outside, the muon system, and the hadronic calorimeter. Quite big technological achievements. This is a picture of the coil. You see this, the person height, when it was assembled on the surface in 2006 and then tested on the surface. This is the electromagnetic calorimeter, and you will have very special lectures on that, so I will not talk more about that. What they use in this particular case, in the CMS, are crystals, which are beautiful devices, which give a very nice energy resolution. Then from, again, to give you the flavor of these of the techniques, this is the tracking detector in CMS. It's the biggest semiconductor silicon detector which was ever built, 200 square meter. Again, before its installation, and finally, then shortly before 2008, in 2008 it was all assembled. You see here the different layers. This is the end cap, this is the beam pipe. The collisions occur inside this cylinder. Atlas is, again, has this cylindrical geometry, but a very different magnetic configuration. In fact, the magnetic field is for the muons in this toroid, as I said before. I will not go into more details because you will hear more. Just to give you a flavor of the collaboration, this is the one I know better, is Atlas. Of course, CMS is very similar. So you see there are really countries, in this case 38 countries, 3,000 scientists which work on it. And in fact, something I want to stress is, of course, when we say work on it, and so in particular young people work on it. So there's a lot of room for students, and the good analysis, and so the physics are made by the students. Well, you see also the gender distribution, which is not perfect yet, but that's what it is. Okay, so Atlas, to show you a little bit more of that, is installed in a big underground cavern, about 100 meters underground, the floor. This is the beams where they collide. Everything had to be lowered down through these shafts. That's how the cavern looked like in 2003, beginning of 2003. A big thing. And maybe one of the most notable parts of Atlas, very expensive part, is this toroid magnet. This is again a sketch of it with the single coils here. There are 8 of them for making the toroid. You have some technical information for it to look after what's in your transparencies. It was a long time to actually assemble them. Pieces were built all over in Europe in industry, and then assembled at CERN in a big hall, and then brought into the cavern. This happened in 2004 and 2005. So this was a long building up of the magnet, and probably this is, unfortunately, in a way, the most famous picture of Atlas. I don't like it so much because, of course, it's nice, it's symmetric, but there are no particle detectors yet installed. So this is just essentially the magnet. Well, there is the calorimeter in the back, and again, I'm sure you will hear a lot about that. So this picture is nicer from my point of view, because this was in 2007 when muon detectors were installed, the calorimeter was installed here. This is an end cap calorimeter, which then at the end will be put inside the magnet as well. And just to give you a little bit of a feeling, some of these pieces were really very, very large. These are the end cap toroids. There are two of them on each side. So they are transported. You see, these were huge transports. And sometimes one also has nice surprises, like, well, nice. There was a problem to actually bring it into the building to lower it down. We had to open a little bit more on the door and things like that. Okay. Just one point I want to make is that it's there's really a lot of high tech, but there is also a lot of maybe less high tech, but very, very important work has been done. For example, cabling. There are about 50,000 cables which go from the experiment to the counting rooms and so on. Of course, then in the tracking devices, this is really all high tech. Now, I think the time is too short to show you I have a movie, but I see time goes on. Maybe at the very end we can come back to the movie, how it was assembled. So just to say that, well, finally in 2008 things were ready, and in fact Peter Higgs was coming for the first time to CERN to look at the experiments, and I must say he's a very modest and humble man, and he said, all this because of our ideas we had, and so he was really just to say one thing is, in parallel to constructing the detector, there was also a lot of work being done in testing at least part of the detector in test beams, of using cosmic rays to again test, and then already making also tests of the software and so of the experiment. So that's one of the areas which is difficult to show, and certainly not in a short lecture like that, but which was very, very crucial also to get the experiments ready. I think talking about the history of the LHC, it would not be fair if I wouldn't say that not everything went as smoothly as it should. There was a big incident just after the startup, namely in beginning of September, single beams went around the machine, and then a few days after there was a connection, supraconducting connection between magnets, which failed because they were not, most likely not correctly soldered. So it was no more superconducting. It heated up, it made an electric arc, and it punctured the helium line. I mentioned helium at 1.9 degree Kelvin. Now, when this gets into room temperature environment, it expands. It expands more than a factor of 1,000. So it was like a bomb in a certain way, and made a lot of damage to 1/8 of the machine, one of the arcs. So there was an interruption then of 15 months. And one can see that people were very anxious when the machine was repaired in November. when it should really start up again. But okay, people were happy. It worked this time. And what they were looking at were actually really the first collision. So in the very beginning, in 2009, one was just colliding essentially the particles as they were injected into the 27-kilometer ring at the same energy as in the SPS, which was the last injector ring in this chain of injectors. So at that time, the collisions were then 900 GeV. And the real joy came really only in spring, then 2010, when for the first time the proton beams were accelerated also. They were accelerated at 3.5 TeV and brought into collision. That was a nice moment. Now, since then, the machine has really worked fantastically well until 2012, well, first month was 2013, and in fact has provided us with 2 times 10 to the 15 collisions. So remember I said that an interesting, for example, the Higgs is 1 in 10 to the 13. So you can already think we should have seen the Higgs because we have had certainly enough. And indeed, that's the case. Now, the excellent performance has made it rather challenging for the experiments actually to operate, because when I said there were actually in this operation were not yet 2,800 but 1,400 bunches roughly in the machine. So every 50 nanoseconds there was a collision of 2 bunches, and not only 2 protons collided typically, but something like, well, this is the distribution, typically 20 protons or so pairs collided. So every time, even if you have an interesting event, you had in addition some uninteresting collisions. And this is here shown, for example, a Z into mu plus mu minus, but then in addition some collisions which we are not interested in. So they are a kind of a background which of course make the analysis a bit more challenging. But again, it worked. So also I should say that of course we are not collecting all these 2 times 10 to the 15 collisions. We have to make pre-selections. And these pre-selections are made with fast electronics, which is called the trigger, which brings down the number of collision events which we record for offline analysis down to a few hundreds per second. So this, as you can imagine, this is also a very important thing. And in Atlas, this is made in 3 different stages. And again, I assume you will hear more about that. Last, before we come to the physics, is really still we have an enormous amount of data, which even with this few hundred events per second, which we collect, there are about 100 million electronic channels in the Atlas or in the CMS experiment. So it's really a lot of data. In fact, of the order of 25 petabytes. And to give you an idea, if one would take CD-ROMs, this would be a stack of 20, 30 kilometers actually with this of information per year. And this had somehow to be prepared as well, how to deal with this data. And this was done by something which is called the Worldwide LHC Computing Grid, which is a dynamic system where the CERN Computer Center, called the Tier 0, where all the 4 experiments from the LHC ship their data, distributes then for each collaboration separately the data into large regional computer centers, and to them the physicists on more than 100 sites connect to make the physics analysis. So that in itself was also a very big development. Just a word about how did this experiment work. Well, this shows you that typically very well. That's in short. You can see this also graphically, for example, for CMS. Essentially 98, 99% of all the channels were working, which I think is quite a big achievement. So now I come to finally to the physics, and just to say, of course, there's a huge amount of physics analysis which are done in these experiments. Many hundreds of papers in scientific journals, and of course I cannot talk about all of them, but they are all publicly available, and you could browse here on this web. I give you just a few examples from a wide range of things. Well, one of the basic measurements is to know what is really the interaction probability that two protons hit, which is called the total cross-section. That's after all giving us all the background which we have to deal with. And well, this has been measured by two experiments very precisely. One is called TOTEM, and also the ATLAS experiment, with a special detector which measures at very small angles. It also measures when two protons do not get broken up, but when they just elastically scatter. This is shown here. And in fact, just to give you an idea, this is somewhat special. These detectors are something like, if ATLAS is at the center here, they are plus minus 240 meters away from the interaction. So they scatter just very slightly, elastically, as one says. Another very important measurement, and giving us confidence that the experiment, on the way to give us confidence that the experiment worked, was already in 2010. That was the first year of high energy operation. One could see, for example, looking at events which produce a mu plus and mu minus, one could see all the history in a way, a large part of the history of particle physics. The Z, the epsilons, J psi, and so on. That was the one I mentioned from the ISR. Now, another very important chapter of the physics is the normal strong interaction of quark scattering, or quark-gluon scattering, or gluon-gluon scattering. Now, quarks and gluons, they are not particles we can observe. Experimentally, what they do is they fragment into sprays of particles, which are called jets. And indeed, one can see, for example, this is a hard scattering of maybe two quarks. And there are two sprays, again 180 degrees in phi, separated of a lot of energy. In this case, each of the sprays, jets, of 2.3 TeV. So this was a collision where the initial collision energy was actually corresponding to something like almost 5 tera electron volts. So that would be a very heavy object if it would have been a resonance or so. Just to, again, a flashback, actually these hard scattering were the first time seen in 1982, again at the P-bar-P collider, where we learned to deal with them. At that time, actually, this is hand-drawn, Okay, again, technology has fortunately evolved. So these are these cross sections, probability to produce such hard scattering at the LHC, at the Tevatron machine at 2 TeV, and that was at the P-B collider before. Now, in the interest of time, I will skip here something and immediately go to a next level of particles we want to measure for proving that actually the experiments works, which is to look at the well-known W and Z bosons. And well, that's how they look like. For example, in CMS, a Z into mu plus mu minus with traces in the muon detectors, or in Atlas, a W decaying into an electron with electromagnetic energy and a neutrino, and the neutrino does not leave any trace. So we can only infer it by what we call missing transverse energy, because it's this electron with a lot of energy is not balanced. So there are millions, 100 millions of such events. They give very clean signals, for example, in E plus E minus or mu plus mu minus at the well-known mass of the Z0. In fact, the signals are so clean that one has to go to a logarithmic scale even to see if there is a little bit of background. Also, the signals, for example, in this missing transverse energy, which is characteristic for the W electron or muon and then the neutrino decay, we see here a very strong shoulder at about 40 GeV, namely half of the W mass. We could only dream of such signals in the 80s when looking and working on the discovery of them. And in fact, just to please Hans, I have shown here the original data when these particles were discovered, just a handful of them, not hundreds of millions. And this was in the UA1 experiment. You also remember these plots, of course, for the W. So one thing one can do is just to measure the cross sections, and this has been done at the 7 and 8 TeV at the LHC. These were the cross sections as measured at the Tevatron machine, and this at the P-B collider at CERN. And the blue lines are the theoretical expectations. I just skip essentially everything about the heaviest particle, the top, which was discovered at the Tevatron and which is, well, maybe I want to say it, which was a very important particle, because to make sure that you understand the experiment, because its final state involves leptons, electrons, muons, for example. It involves missing transverse energy because of neutrinos, but also jets and also bees. Bees are these quarks which have a finite flight time. So combining all these things gives you a handle whether actually you understand your detector does what it should do or not. And indeed, again, one can see here measurements of the LHC, which has been operated at 7 and 8 TeV, compared with what we expect theoretically. Certainly a good agreement. This here is the 2 TeV where actually the top quark was discovered. So the punchline on this is that one has measured really over many orders of magnitude such standard model particles, W's, TT bar, and so on, also pairs, for example, of W's or so. One can compare them with the theoretical expectation, and there is a good agreement. And this excellent performance in standard model measurements, of course, gives one confidence that one is ready now to make a discovery. And let me now use the last 10 minutes for the Higgs, really. It's a complicated story in a certain sense, because the Higgs can be produced in different mechanisms. Remember these Feynman graphs. And characteristically, the Higgs decays, well, proportionally to the mass of the bosons, in this case here, for the W and C, or also proportional to the mass of the fermions, for example, BB bar, or the tau leptons are, for example, fermions. It's a bit more complicated for the photons. So this was what was expected when taking the theoretical calculations from the production, the different production mechanism and the different decays, and then you could predict that, for example, the black line here, depending on the mass, that should be the cross-section times the branching ratio, so that's what we should observe, the number of events we could calculate for different final state configuration as a function of the mass. So what did we observe? Well, let me start with the simplest, not for the calculation, but for seeing it, and conceptually simplest topology. That is the Higgs decaying into two photons. This is shown here in an event from CMS, where the green is the electromagnetic calorimeter, and these are the signals in the crystals, so to speak. And the length is proportional to the energy. So with the length be the energy and the angles, one can then recalculate the mass. And what one observes here in Atlas is, well, there are, as a function of the mass, there are such events which are normal ones, and then there is an accumulation of events at about 125 GeV. If one subtracts this smooth curve, this is the signals coming out, and very similarly from CMS and at the same place. And again, that's of course very important, that in the case of Atlas, you will hear about that from Isabel certainly, it's a completely different calorimeter, it's a liquid argon calorimeter compared to the crystal calorimeter of CMS. But yet the result is the same, and that certainly is a very strong message. Another decay mode of the Higgs, which was useful for the discovery, is the decay, the Higgs in two bosons, two Z's. Now, as the Higgs is relatively light, it turns out, but we didn't know before, of course, these two C's cannot be real, because the C is 92 GeV, so, and the Higgs is only 125, but it can still, virtually, for a short time, it can decay into a Z, which in turns anyhow decays either into electron pairs or muon pairs. So this example here is where both of these C's decayed into a muon pair. And what do we observe? Well, if one plots, again, as a function of the 4 lepton mass, one gets a distribution which looks normal from the normal standard model processes. You may think, why do we see a Z? You can ask later on. This is what we expect from the normal processes, and in both cases, clearly there is something new showing up, again at 125 GeV. So in both experiments. Now one can look at more complex, complicated decay modes. It can also decay into two W's. Now the two W's, each one, for example, this can decay into electron neutrino, the other into a muon and a neutrino. So there's a lot of missing transverse energy in the event. And it's a bit more tricky to find variables where one would not see such a narrow mass peak. But there are variables called, for example, transverse mass, where again one sees clear accumulation of events on top of what is known from other standard model processes. And if one subtracts these known processes from what one observes, one sees an accumulation of events. And so on, even more difficult in some other channels, which I will skip. So what one has really observed, first of all, is a peak at the mass, now taking all these different channels, which is about 125 GeV with these errors in Atlas and with these errors in CMS. So that's very well, of course, in agreement. And one can ask oneself, for example, the question, what is the probability that this was just a accidental occurrence? And this probability, accidental occurrence that the background has fluctuated, well, this probability is really very small. It's something like 10 to the minus 24 or so alone in the Atlas experiment. So clearly there is a new particle. One can see that this new particle has actually what is called signal strength, which is essentially the cross-section measured compared to the cross-section we expect from the standard model. Should be 1 if it's a standard model Higgs. This indeed is within the errors well around 1. Now, just two more things about the Higgs. Well, what would we expect from a Higgs? Well, as I said, it should couple proportionally to the masses of the particle in which it decays. And if one arranges this in such a way that one expresses it in the coupling strengths on this logarithmic scale of the masses, they should fall on a straight line. These are the heavy guys, the top, WZ, and then the light ones. Still measured with very big errors, but so far it is indeed confirming what we expect for the Higgs. One can also now look at the angular topology, how these events decay, and from that one can infer its spin. And one can test whether this spin is compatible with being 0, a scalar, boson, or whether it's eventually another spin. And it is compatible certainly with the spin 0, and these other hypotheses, the wrong ones, can be excluded to a high level of confidence. Not yet so high, not 10 to the minus 23 like the occurrence of the signal, but already very high. So these type of studies will be of course continued. And just to tell you, it's really, that is what in '99 one was hoping to see in terms of significance over the whole range. We didn't know whether the Higgs is 100 GeV or 1 TeV, and that is what in July 2012 we observed. In fact, as I say, the dream became true faster than anticipated. Maybe on the Higgs story you should also know that at this lower energy machine, at the Tevatron, they tried very, very hard, and almost, well, at the level of 3 standard deviations actually got a signal compatible with the Higgs. Clearly, I think they would not have been able to claim that this is a Higgs signal without having the confirmation of the LHC, just because we had much more energy and much more intensity to produce them. But one thing which was very remarkable on this previous experiment in the Tevatron is that they have really improved, and that's the message. If one is clever, improving the analysis method, you can be much more sensitive to find something new than just brute force what you would expect from having more data. These were the lines one would expect how significant they should get. One would be able to observe it if one just would accumulate more data. But as you can see, they have done much better by actually having improved their analysis. And I think similar things are, of course, the challenge for all of us for the future. So here you see how the signal came in 2011 and 2012 run. In July, that's where the discovery was announced, and then up to the end, it even became much clearer. Okay, so I think I was much too optimistic. I wanted to tell you much more about the future also, and so, but I think I have used now this 1.5 hours, and you can see the rest of my talk, which I will be available on. You put it on the web, or yeah, you can see it on the web. And okay, it's not. Let me just say that this is, of course, not the end of the story. The LHC has actually only produced about 1% of the collisions we foresee until 2035. And also, we have been operating the machine only at 4-on-4 TV because of being cautious about these connections between the magnets. One didn't want to reproduce another incident. And what has been happened in the last 2 years was all these connections have been remade, reinforced, checked. And so we will now in April start at the higher energy at 13 TV, still to be a bit cautious, and then going to 14 TV probably in the next years. So there will be a huge potential of hopefully other discoveries coming from the fact that we have more collisions, but also from the fact that we will have a much higher collision energy, so we can make more heavy particles which we still hope to find, and to find a clue maybe for the dark matter or something like that. Okay, I stop here.